Hello, this is Mr. Craig, and I want to go over our first lecture here, discussing scientific method and just some of the basics for science. I apologize, I am not a big fan of PowerPoint presentations. I actually despise them very much, and I'm sure that a lot of you feel the same way. But my first couple of lectures will be from PowerPoint, but again, after the first couple, you'll never see another PowerPoint from me. All right, well, let's talk about the steps of scientific method. The first thing that we need to do, since this is a science class, we need to talk about the steps involved in scientific method. The first thing that we want to recognize is that as a good scientist, you're going to make a lot of observations. You should be very, very good at making observations if you plan on being a scientist or just somebody that's very observant. There's two types of observations. There's quantitative and qualitative. The quantitative is with a number and a unit, and the qualitative is without a number. So you might say, oh, Shelley's shirt is red. Okay, that would be a qualitative type of observation. There's no number involved there. A quantitative type of observation might say that, oh, we got 7 inches of snow last night. Okay, that's an observation with a number and a unit. So once we have made our observation, then hopefully we should be thinking about how did that happen, or why did that happen, or where did that happen. So the observations will formulate a hypothesis to answer the why question. It's a possible explanation for the observation. We will design some experiments, or you can try to recreate what you believe to have happened based on your hypothesis by gathering new information to decide whether or not the hypothesis is valid or true. Outcomes over the long term. There's a theory and a model, a set of tested hypotheses given an overall explanation for some natural phenomenon. Natural law deals with the same observation, applies to many different systems. So like when we talk about laws and theories, we'll talk more about that. But the one example that chemistry deals with is the law of conservation of mass. That's when balancing out your equations, make sure you have the same number of atoms on both sides. But that's a natural law. We don't have to come up with a brand new hypothesis. We just know that that's what happens for many different types of systems. Law versus theory. Sometimes we get caught up and we try to argue a theory, or we try to argue a law and we think it's a theory. But what a law does, it summarizes what happens, like the law of gravity. It's pretty hard to dispute that gravity is present. Now, you can be a non-believer if you want to be, but if you plan on climbing up to the top of a tall building and testing the law of gravity, then try it out. I mean, hey, you never know. There might be a nice strong gust of wind that comes up. A theory, however, is an attempt to explain why it happens. So when we talk about and this is, a lot of people love to argue this for some reason. I'm not sure why. But the theory of creation versus the theory of evolution, unless you're able to make an observation and see it take place, you're wasting your breath as a scientist. So theories are not things that we really want to spend our time arguing, but laws we can definitely support and argue for. So there is no evolutionary law. There is no creationary law. And as scientists, we don't want to get into that arguing theories. Okay, that's my little soapbox speech for a second. Nature of measurement. Measurement has two parts. A quantitative observation consisting of two parts. The first part, obviously, is the number. However, what a lot of you do, or you will find yourself doing this, is you'll stop right there. So we always have to have two parts of a number, two parts of a measurement. There's a number and then its unit. So when we talk about the number in a unit, I might walk up to you and say, and I'm a rather large individual. I'm not a fat individual, but I'm 6'2", and I have a nice build. If I were to play football, I could definitely pass off as one. But I might walk up to you and say, I weigh 110. And a lot of you, especially those of you who know me, might kind of giggle and snicker and go, 110? There is absolutely no way that you weigh 110. However, what I'm forgetting to do is put the unit on here. And by not having a unit on there, some of you don't realize that I'm actually talking about kilograms. So kilograms is a lot larger unit of mass than a pound. So just because we're so familiar with our own dialogue of saying, oh, how old are you? Well, I'm 17. Well, 17 what? Days, years, decades? And again, we kind of get in the habit of leaving the unit off because we already know what everybody's implying. But as scientists, we never ever want to imply. We want to be specific. So we always want to write down the number and the unit. So like for example, if I were weighing out a sample of copper, I wouldn't just say, oh, that weighs 20. Be specific. Tell me what the units are. And especially when you're doing your homework and your math problems, especially when we talk about dimensional analysis a little bit later on, you don't just want to leave a number and walk away. You always want to write the number down with the unit because you'll lose points, and I don't want you to do that. All right. I'm not going to try to pronounce this because I don't speak French, but it's the international system or the metric system. And we should be able or be familiar with the metric system, like kilograms, meters, Kelvin, moles. Those are things that you should have been exposed to by now in general chem. Amps, we'll talk about a little bit later on, near the end of the year, well before spring break, but probably right around Valentine's Day. Kelvins, everybody should know Kelvin. Seconds, we don't have to worry about because we use that every day. Oh, shoot. Let's see. Uncertainty in measurement. Whenever and this will have a lot more of an application when we start getting ready for the AP exam, more than doing our homework. But whenever we're not sure about a measurement, and it's hard to actually explain this over PowerPoint without you looking at something here, we always write down the values we know. So if you know what a graduated cylinder looks like and how it's marked off, typically it's marked off in usually about every 2 to 3 milliliters. I'm not exactly sure. I don't have a graduated cylinder in front of me right now. But we have to write down everything that we know, but we only estimate, not guess, we only estimate on the last value. So we might say, oh, I know for sure that I have 8 milliliters of water, but it's kind of in between two other marks. So that's my estimation. I write down the 8 milliliters, and then that point whatever, maybe 8.5, the half is my estimate, not my guess. It's a very educated guess, but it's my estimate. So we always write down everything that we know, but only one uncertain value. Okay. All right, precision and accuracy. Here's another term that we use a lot, or use two terms that we use a lot to typically mean the same thing. Accuracy refers to an agreement of particular value with its true value. Precision, however, refers to a degree of agreement among several elements of the same quantity. All right, what does that mean? Here, I've got a nice little demo here. Okay, here's my little smiley face. Okay, I'm calling it a target. And what I want to do is I want to break out my not machine gun, but my rifle. And I'm not a very good shot. I would be terrible if I had to survive or rely solely on hunting of animals to survive. It would be bad. But let's say that I'm looking through my scope and I want to put a nose on the happy man. Okay, so I'm looking through the scope, and again, this is a rifle, so it's a long gun. And as I'm looking at the crosshairs, it lines up right here. In other words, if you ever think about, if you've ever shot a gun before, you've got your sight, which is round, and then it has a stick, and then you always want to put the circle on top of the lollipop. You want to make a lollipop. And again, I might be talking about some things that some of you have never, ever experienced, and actually that's a good thing. I don't want you to go out and buy a gun and start shooting up things. But let's say that I've got my target, and I'm aiming at this spot right here, where would be the nose on the happy face. So I've got it lined up, I'm poised, I'm breathing right, I'm relaxed, and I fire off 3 shots. Once I fire off the 3 shots, they hit right here, boom, boom, and boom, okay? And then I go, uh-oh, I was aiming right here, but this is where my bullets hit, okay? Then I give the gun to somebody else who's a much better shot, has much better mechanics and form than I do. And they line it up again, same way, looking right where the nose would go. And they fire off 3 shots, except they hit them, boom, 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 right in the middle of my triangle. And then I give it to some more people, and they're all shooting in this general area right here. Is the gun broken? Is the gun got a twisted barrel or a bent barrel? What's happening? We're aiming right here, but everything's hitting on the target right here. Well, we can obviously say that the sight is not accurate. Oh no, the sight is not accurate. However, the sight is precise. And this is good data if we were saying, okay, we're aiming for this spot right here. Everybody's aiming for that spot right there. However, we're all hitting in this spot right here. So we're getting something that is consistent. We're getting the same type of measurement. It's just like saying, okay, if I want to lose 10 pounds real quick, I'll go into my bathroom scale before I step on it, okay? Or actually, I could step on it and read out, it says 220 pounds, okay? I want to lose 10 pounds right now. What do? Well, I step off of the scale, and I bend down, and I actually spin the calibrator or the weight adjuster back 10 pounds. Step on it, now it says I weigh 210. Woohoo! I just lost 10 pounds. Did I really lose 10 pounds? No. I made it so it's precise instrument now instead of an accurate instrument. So if I want to make my wife really happy, I say, hey, hon, come in and weigh yourself. And she gets on the scale and she weighs 10 pounds less. She's happy. She leaves. I tell my son, hey, come on, Sam, come on in here, weigh yourself. He gets on the scale and he's like, what happened? I just lost 10 pounds. No, not everybody has lost 10 pounds, but we're reading a scale that always reads 10 pounds too little. So it's something that we can measure, something that we can rely on. So if everybody in the world wanted to weigh themselves, all I have to do is say, hey, the scale is off by 10 pounds. And everybody knows exactly how much they weigh. Okay? So this is an example of precision. And so how would I fix the gun if I were able to adjust the barrel? Would I change the sight so I'd aim right here to hit the bullseye? So I'd point my gun right up here. Well, if I were to do that, I'd hit over here. Okay? So really what I want to do is I want to aim right here if I don't want to change the sight. So if I aim right here, then I'd hit it right in the middle. It's kind of a crazy way. So if you're ever out hunting and you want to hit, say like say you're going rabbit hunting, Bugs Bunny. You see the rabbit tracking across, and then you go, okay, right about the point where you're ready to shoot. Once it gets to this center spot right here, you're going to track it. Then you're going to drop your gun down real quick, fire off a shot, boom! Now you hit it. Okay, that's not probably the best way to hunt. So when we talk about accuracy, if we fix the sight and we aim at the bullseye and we fire off a shot and we hit it, it's accurate. So that's the true measurement right here, and we're actually aiming at the spot that we're hitting the spot that we're aiming at. So the difference between precision and accuracy, you got it right there. Okay? From the current slide. All right. So we did precision and accuracy. All right, rules for counting significant figures. Ooh, you guys are going to love this. Non-zero integers. We have zeros, leading zeros, captive zeros, trailing zeros, and exact numbers. These are what we're going to talk about. All right, the first thing we want to talk about is non-zero integers. Things other than zero are always significant. Okay? So, if I look at this number right here, 3,456, how many significant figures does this number have? Well, since there's no zeros, all of them are significant. So there's 4 sig figs. Okay? 27 has how many sig figs? Well, since they're both non-zero numbers, there's 2 sig figs. Okay? Zeros. When we look at leading zeros, we do not count as significant. Now, it might be kind of strange to think about if I wanted to write the number 100, I wouldn't write 00100, but you could if you wanted to. Leading zeros obviously do not count as significant figures. So if I have, say, a number that we would normally write, like this value right here, these are simply placeholders. They are not significant. So there's really only 3 sig figs in this value right here. These right here don't count. Okay, so leading zeros do not count as sig figs. All right. Captive zeros always count as significant figures. So whenever we have a value that has a captive zero, that zero is now significant. So how many sig figs in this number? There should be 4. Okay. How many sig figs are in this one? Well, all of them. So what is that? 10? Yeah. Okay. So captive zeros are always significant. All right. Trailing zeros are significant only if the number contains a decimal point. So if I look at, say, this number right here, I've got 9.300. These zeros are significant because there is a decimal point. That actually, we have a non-zero number, okay, we have a decimal point, then we have a non-zero number before or to the left of our first zero. So all 4 of these are significant. If I look at this one, commas are not decimal places. So there's only 2 sig figs here because there is no decimal here. If we had a decimal at the end right here, then they'd all be significant. But since these are commas, there's only 2 sig figs. Okay. Alrighty. Exact numbers have an infinite number of significant figures. In other words, we never ever use conversions to determine how many significant figures we have. So like, for example, you'll be given this conversion, 1 inch equals 2.54 centimeters. We never ever look at a conversion and say, oh, well, since the 1 inch has 1 sig fig, then we're going to base that on how many sig figs our answer will have. Don't ever do that. And we'll talk more about that later on in the year. All right, multiplication and division. Whenever we multiply and divide values, what we want to do is we want to look at the number that's given that has the least number of significant places or significant figures. Based on that, we will then determine how many sig figs our answer will have. Okay? So we always want to look at the least precise measurement. So for example, I have 6.38 times 2.0, and my calculator says 12.76. However, since I'm writing my answer with the correct number of sig figs, I want to give this answer only the correct number of sig figs. So looking at 6.38, how many significant figures do we have? There are 3. Looking at 2.0, how many significant figures are there? There are 2. So my answer, 12.76, should be rounded to only have 2 sig figs. Now, since this 0.7, in other words, if I stopped right here, 12 would be I only need this number right here. However, we don't truncate in chemistry. We round. So my final answer should be 13. Okay, or have 2 sig figs. So always round up and we'll round down or leave it alone. So again, multiplication and division, the value that has the least number of significant figures determines how many significant figures our answer will have. When we finish, we always want to type everything out, and we never want to round anything until the absolute last step. All right, when adding and subtracting, a little bit different. When adding and subtracting, we want to look for the value that has the least number of decimal places. The least number of decimal places. So when we look at the number of decimal places, that tells us how many decimal places our answer will have. Okay, so everything to the left of the decimal we don't care about. We only care about to the right when we're adding and subtracting. So looking at this value, we have 6.8 plus 11.934. And again, on my calculator it says 18.734. Need to do that. Type that all in, get that value. However, when you write the answer down, you need to look at which of these two numbers, since we're adding, which of these two numbers has the least number of decimal places. So how many decimal places does 6.8 have? 1. How many decimal places does 11.934 have? 3. So our answer should have 1 decimal place. So we should write down 18.7. And that's for 1 decimal place. All right, dimensional analysis. What I'm trying to say here is make sure that the values are equal to each other. In other words, 1 kilometer is about 0.62137 miles, or 0.62137 miles is 1 kilometer. What is not okay is to write down that the ones are always on top and the conversion is always on the bottom. That's wrong. Okay? Make sure that your conversions are correct. And typically I'll give those to you. Or you will have to be able to do the metric conversions on your own. Okay? Temperature. We'll use Celsius scale. We'll use Kelvin scale. We will not use Fahrenheit in class to work out problems. The only time you'll ever hear me discuss Fahrenheit scale is when I'm saying, okay, well, what's the temperature outside or whatever. That really is the only time I ever use Fahrenheit scale. I won't ever use Fahrenheit when working out a problem. You'll never have to do a conversion from Fahrenheit to degrees Celsius. You will get to do Celsius to Kelvin conversions, and we'll talk about that later on, which is right now. So the Kelvin scale, again, if you know the degrees Celsius, add 273. If you know the Kelvin value, subtract 273. And we'll do that again. And when do we use kelvins? Typically, gases, right? We always have to have Kelvin scale for gases. All right, density. Again, density is mass over volume. Okay, and the mass can be in any unit. The volume can be in any unit. Typically, we go grams per centimeters cubed, or we can go grams per milliliter, kilograms per cubic meter. There's many different things, so just make sure that you're giving the proper answer with the correct units. Matter, anything occupying space and having mass. Okay, so does air have matter? You better believe it. Air has a lot of matter in it. We really, as human beings, don't understand how immense and how strong and how important our atmosphere actually is, even though we'll talk about gases a lot later on. Classification of matter, there's 3 states: solids, liquids, and gases. Again, solids are rigid, fixed volume and shape. Liquids are definite volume but assumes the shape of its container. Gases, there is no fixed volume or shape, and it assumes the shape of its container. Types of mixtures, there's homogeneous mixtures and heterogeneous mixtures. We'll talk more about the homogeneous and heterogeneous mixtures a little bit later on. Just know that when we look at a homogeneous mixture, an example is air. That's probably one of the better ones. No matter, as long as we have air, the percents that make up the air, like the nitrogen, which is about 78 to 80%, oxygen's about 18%, carbon dioxide's about 1%. No matter if we have atmosphere or we have air, those percentages are the same, regardless of how thin the air is or how thick the air is. So those percentages are very, very consistent. However, when we go higher in altitude, the percentages stay the same, but we don't have as many of those gases. It's just like if you jump in a swimming pool. You dive to the bottom of the swimming pool, your ears may pop because you have the mass of all that water above you pushing down on you. Same thing with air. It's a sea. So the higher we go in the altitude, we don't have as much air pushing down on us as we do at sea level. That's why we feel good at sea level, because we have a lot of air pushing down on us. So we like that. Heterogeneous mixture, if I shake it up, most of the stuff will settle to the bottom. That's probably one of the better examples of a heterogeneous mixture. And it's not uniform. Okay, the percentages change. Yeah, so we'll leave it at that. Compound, obviously it's a substance of constant composition. It can be broken down into elements by chemical processes. An element, that's as small as we can get without destroying the actual atom itself. So make sure you know the difference between a compound and an element. All right, so that concludes the first lecture. I think you should be able to do the homework here. I do want to make sure that you know this, the Great Mega King. Let's see here. I don't know if I have it up here. Let me see if I can type. Let's go back to real word here. Okay. Okay. Whoops, get back. Okay, I'm going to try to see if I can get this to work here. Maybe if I make a table. I apologize. I know this is going to take the video a little bit longer. Oh, crud. Insert table. There we go. I think this might work. Probably need a few more columns here. Don't want to do that, sorry. Okay. Well, no, let's just do this. The Great Mega King one day caught me. Oh, I don't have this. Insert. Symbol. Microwaving nasty pizza. Okay. All right. These are all 10 to the whatever powers, and let me, and again, I apologize for this. 10 to the 12. Grr. 10 to the 9. 10 to the 6. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, of course. I'm short one. Figures. I don't know if I can copy. Oh, I did. Okay. Let's do that then. All right, got it. Here we go. Boom. I know you're enjoying this. Sorry. Okay. The Great Mega King one day. It's a short D, little k. Hang on. One day caught me microwaving nasty pizza. Okay, and these are all right. -9, -6. You guys are very patient. I'm so sorry. Oops. All right. Now, what I'm actually creating here is a metric conversion for you. And these are the ones that you need to know. Now, I know that some of you have had learned more in general chem. You know what? That's good. Nothing wrong with that. I don't want you being upset with your chemistry teacher saying, hey, I had to learn more. Nothing wrong with that. I like you guys when you learn more stuff. Trust me. It makes you a better human being, better person. All right. So here we go. What this is tera, giga, mega, kilo, 1, obviously. Deci, centi, milli, micro, nano, pico. Now, the saying that I was making here, and let me make this a little bit smaller here so everybody can see. Okay. What I was doing was doing a little saying that somebody quite a few years ago gave me. The great mega king one day caught me microwaving nasty pizza. Okay, and these are our conversions, our metric conversions. That tera is 10 to the 10, giga 10 to the 9, mega 10 to the 6, kilo 10 to the 3, 1. Anything to the 0 power is 1. Deci negative 1, centi negative 2, milli negative 3, micro negative 6, nano negative 6. I'm sorry, negative 9, and pico negative 12. All right, so when we do conversions, if I say that I have 1 tera meter, and I want to know, okay, how far is that in kilometers? Okay, well, when we do our conversions here, and actually let me see if I can insert, might be able to, I don't know if I can or not, probably won't be able to. Okay, I can do it. If we say that we have 1 terameter, we always start with what we know. Okay, we always start with what we know. So we have 1 terameter, and we're going to multiply that out. And we'll put another little bracket on there. We're going to put terameters down below, and since we're looking for kilometers on top, then what we're going to do is we want to assign whoever is larger of these 2 units the value 1. Okay, so when I look on my scale here, or my table, I notice that tera is bigger because it's farther to the left. These are bigger than these over here. Picos are pretty small. I've never seen 1 picometer. I don't know if I've seen 1 terameter, to be honest. That seems to be pretty large. However, if I'm doing a conversion, I want to make sure that the value that is greater, is larger, is assigned the value 1. Okay, don't just say it's 1 because it's on the bottom. Now, do recognize that when we do dimensional analysis, the value that we started with, in this case terameters, needs to slide diagonal. We want to cancel out terameters. If we put it straight across, we're going to have terameters squared, and I don't know exactly what that is. It is pretty big. And then looking at kilometers, we have to ask ourselves, okay, well, how many thousands or how many zeros are there from kilo to tera? Well, if we look at tera, it's 10 to the 12, kilo 10 to the 3. So I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that's enough. And then kilo is 1, 2, 3. So how many times did I move the decimal place from here to here? I think I need 1 more 0. So the answer is to get from here to 1,000, okay, or actually from 1,000, so I'm going to go 1, 2, 3. How many more places do I need to move the decimal? I should have to go 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what that means is when I look at my value here, there are 10 to the 9 kilometers in every terameter. So when I finish, okay, it just so happens that that number is going to be the same, which is nice. This is a real quick calculation, and it doesn't want to cooperate, which is fantastic. And of course, you want to put your units on there. Okay, so when we do our dimensional analysis or our conversions, make sure that we are showing our work, showing our units. Let's say we do another one here. I apologize for the length of this video. Let's say that I want to go and see how many, click on there, come on guys. Maybe I'm not going to be able to. How many gigabytes are there if I had, say, pico, okay? So the exponential distance from pico to giga is not 12 minus 9, but it's actually 9 plus 12. So in that case, I would have 10 to the 21 for the pico, where I'd have the 1 for the giga. All right, I'm going to cut this video off because I know it's getting a little long and a little overblown here. So I hope this has helped. You should, all the information I've talked about here, plus all of your previous knowledge from General Chem, should allow you to do the first homework assignment. And again, if you have any questions, don't hesitate. Be sure to email me. And as always, I hope this video has helped.